Hi everyone, I'm back again. I'm here to do LeetCode problem number 46, which is permutations. Let's get started. Given an array nums of distinct integers, return all the possible permutations. You can return the answer in any order. This is not a hard problem to understand. You're given an array as an input, 1, 2, 3, and you return all the permutations. So you have 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. This is, of course, 3, an array of 3, an array of 3. This is, of course, an array of 2. And the answer is 0, 1, 1, 0. As well as this is just a array of 1, and the answer is 1. As you can see, this is a list of lists. And moreover, if you take a look at the number of elements in the answer, it's n factorial. So this is 3 times 2 times 1, which is 6. And you have 6 entries in the answer. This is, of course, an array list or an array with 2 elements. So that's 2 factorial, 2 times 1, which is 1, 2 number of elements in the answer, and 1 factorial is obviously 1. It's not a hard problem. This is a backtracking problem. Let's take a look at the constraints. This is nice. We know that the input array has a length of it's between 1 and 6, which is good, which means that it's also not, the length of the array is not going to be something too crazy. Moreover, you have the values themselves within the array can be as low as -10 to as high as 10, which is also not a crazy range. Lastly, we have that all the integers of nums are unique, which is pretty helpful. So this is, of course, a backtracking problem. But let's take a look at it anyway, what the topics are. Okay. This is an array or backtracking. Okay. So there's 2 things that we need to do with regard to this algorithm. So the first thing, I'm going to just call it milestone number 1, is to set up the skeleton of the program. And milestone number 2 is to define an auxiliary function backtrack that will perform the backtracking. Okay, so those are the 2 things that you have to do. And let's start with the skeleton first. Define a result list res that will hold the answers. Call define and call the backtrack function with parameters res, an empty list, and nums, which is what we pass in. Then the last thing is to return res. Okay, So this is what we're going to do right now is that res equals an empty list. We're going to call a function that we have not defined yet called backtrack. Actually, I'm going to do something a little bit different. Okay. I'm going to do something different right now. I'm going to do res equals the list, and then we're going to do backtrack of res, an empty list, and nums, and then we're going to return res, okay? And backtrack should be always self.res, self.backtrack, I mean. So this is basically the skeleton, and I'm going to define my backtrack function right here, def backtrack self. I'm going to call this a container. I'm going to call it result actually. I'm going to call this a temporary container. And then I'm going to call this nums. That's going to be the backtrack function that I fill out to do the actual backtracking, right? So this is basically the skeleton. We define the signature for a backtrack function. We define a results list. We call the backtrack function with the results list an empty list, and which is going to hold the current permutation as well as the nums array that we're given, and then we're going to return res. So let's define the steps for milestone 2. Check that the length of the temporary of the container. I'm not going to call it temp container. I'm just going to call it container. Check that the length of the container is equal to the length of nums. If so, return append a copy of the container to the result. Then what we're going to do is define a for loop that goes from 0 to length of nums within the for loop. Check to see if the current value indexed by I is in the container. If so, continue. If not, append the value in nums index by I to the container. And this is the call the backtrack function. And this is the key. Pop the rightmost element from the container in so that the recursive calls to backtrack can find all the other permutations. Okay, so let's do it. Check the length. Actually, you know what? I'm going to move this to the bottom because this may be a bit easier. Check that the length of the container. So if length of container is equal to length of nums, then what do? Is that you do result.append the temporary container. You append the container and then you do return. Okay. For I in range len nums, you then do within the for loop, check to see if the current value indexed by I is in the container. If so, continue, right? V equals nums I. If V in container, continue. If V is not in container, do container dot append V, and then you call backtrack on result container nums, and then what you do is you do a, actually you don't need the space right there. You do a container, wait, not a container, yeah, container dot pop. So essentially what you're doing is this is the auxiliary function that if the length of the container is equal to the length of nums, you append, we found a permutation, and you append the permutation to the result and you return, and because this permutation was found and this path along the backtracking is done, then you do a for loop from I equals 0 to up to length of nums. You get the value that's encoded with this index, and if the value is already in the container, then you continue. Else, you add the value to the container and you do a backtrack operation. And lastly, this is the one that's always confusing, is after the backtrack operation, you have to pop a value from the container so that the recursive calls can find all the other permutations. Without this operation, it's just not going to work. So let's try it. Oh yeah. This has to be moved before. Right. Okay, so give me a second. I can't submit right now. Okay, I'm going to try submitting again. Okay, and it works. There we go. The time complexity is O of n times n factorial, because that's the number of permutations that you have. And the space complexity is O of n, because the worst case scenario is that you have n recursive calls on the runtime stack, okay? O of n factorial, time complexity, O of n space complexity. This was an interesting problem. It's not as challenging as some of the other backtracking problems I've seen, but it's a good practice. And so I'll see you at the next one.